Hi, y'all. So we're going to be starting up a new class, basically, and we are in electromechanical energy conversion. And this first problem that we're going to be going over are really magnetic circuits. So right here we have this transformer core, and I guess we can just kind of get started with the question. So it says a magnetic circuit provides flux into two air gaps. So we have the air gap right here, the air gap right here, varying. They have different lengths. Also, we have coils N1 and N2 with 700 and 200 turns respectively, and they're connected in series and carry a current of 0.5 amps. It says neglect leakage flux, reluctance of the iron, since the infinite permeability, it has an infinite permeability, which means mu r, or I guess, yeah, mu r. The relative permeability of the core is infinity, and fringing to the air gap. So we don't have to worry about fringing. So this also means that the area of the core is equal to the area of the air gap, which is important for us. And here it says determine the flux. So we need to find A, the flux of the air gap, and B, the flux density in the air gap. So we need to find B and that flux. Okay, so really what we want to do first, what I've come to, do first in these types of problems is draw our magnetic circuit, our circuit model for this transformer core. The way we're going to do this is we have to model this transformer core in terms of resistance and also the air gap in terms of resistance. Now, what we're going to notice here is I'm going to draw this. Sorry, not resistance, reluctance. Sorry. So you're going to see this R term get thrown around a lot. This is going to be reluctance. The unit for reluctance is amp turns per Weber. So one thing I'm going to say for this class, at least the professors kind of already made this apparent, is units will be very important. So we have reluctance, and then we have flux, which is in Webers. And then we have the magnetomotive force. Sometimes you'll see me write it as MMF. This is going to be in units, if I remember, amp turns. And this is very similar to your Ohm's law, V equals IR, because we have magnetomotive forces equal to the flux times the total reluctance. I'll rewrite this as MMF total. Okay? So these three equations here are very important, or not equations, but units especially are very important because they're kind of the building blocks for our circuit models and our transformer models for this type of class. So first we have this reluctance, this air gap reluctance, and I'm going to call it RG1 because we have two different ones. And now we have another reluctance, and it's going to be, and of course I'm going to be writing this as resistance because it's a circuit model, but the reluctance of the transformer core for path A, B, C, D is going to be here. I'm taking the mean path, which is what this line, this dashed line is. And now, what do we have next? Well, we have this middle part right here. I'm not going to get there yet. I'm going to do that on the last part, but what we need to do is the right branch. It's going to mirror the left branch. We notice it's the exact same type of core. It's symmetrical. So we have this reluctance, which I'll call as AFED. And if you're wondering where I'm getting these letters from, they're in the problem or in the figure here. A, B, C, D, A, F, E, D. Okay. And now we have another air gap. So this is going to be air gap 2, reluctance air gap 2. Now, what about the middle branch here? The middle branch is going to be a little bit different because these wires with current flowing through them will induce a flux. This is going to be our quote unquote voltage source, or our MMF, our magnetomotive force. So the magnetomotive force of the first winding is going to be equal to N1 times I1. Now, I1 and I2, they're not going to be different, so I'm just going to leave them as I because there's only one current flowing. We can see here that they're connected. We see N1 and N2 are both connected, so they have the same current flowing through them. Now, what is this? The number of turns in 1 is 700 times the current 0.5. So this is equal to 350 amp turns. And this is how you get your units. Current in amps, or sorry, turns in, number of turns in turns, and current in amps. Now, what about MMF2? This is going to be in 2 because we have another set of turns times that same current because they're connected again. So we have 200 times 0.5, 100 amp turns. Okay. Now, what else do we notice? Well, we also have a core in, being wrapped around by this um, wire. We have another path, is what I'm trying to get at. We have another path, which means we have another reluctance. So our reluctance, our final reluctance, will be this one here. We'll call it reluctance AD for the path AD from A to D. We have to take into account each branch, just like you would for any circuit. Now we have to worry about these MMFs. These are going to be your voltage sources. Now, how do we know what the polarity is for these quote unquote voltage sources? Can we just throw out plus minus plus minus? Not exactly. We can't do this here. I'll label this 1 and label this 2, but the polarity of these is going to be what's it called? Sorry. The polarity of these is going to be solved for by looking at the flux, the induced flux from the current going through the wire. Well, what do we know about current going through a wire? That's just in general. Well, it produces a magnetic field. Now, if you wrap around a wire, a current carrying wire around a ferromagnetic core, it induces a flux. This flux, you use your right hand rule. So your thumb goes in the direction of current. I've gone through this in circuits and systems in a video before. If you want to go back and look at that, you can. This is going to be the same concept. Your thumb will be going in the direction of current for I through N1. Now, which your your palm will be facing the direction which the core is at. So if we see here, we can see the line of wire above the core. That means the core is underneath the wire. That means your palm is facing down. So whenever you do your right hand rule, thumb going in the direction of current, palm going in the direction where the core is with respect to the wire, we know it's facing down. So now you make sort of a thumbs up. You wrap your fingers around, and you notice your fingers are coming around and doing this sort of motion. They're going up. So that is the polarity of our voltage. That means positive will go on the top and minus, the negative, will go on the bottom because your fingers are wrapping to the top. Now let's do that for the second voltage source here. We know the current is going this way, then it's going this way, going down, left, right, left. I must be special, sorry. It's always going right. And now it's going left. Now it's going down, and now it's going to the right. So it's going to the right still, right? It's going to the right, and now we see it's going to the left. The current through the wire is going to the left. So on this wire right here, the current is going to the left, so your thumb goes to the left, and the wire is above the transformer core. So now your fingers wrap around and they point downwards. So now this one is opposite polarity. So now we have a plus minus. Okay, hopefully that made sense. If not, you can go to the previous circuits and systems video and you'll find it there. But now we know this is 350 amp turns, and we know this is 100 amp turns. And in total, we have 350 minus 100 is 250 amp turns. So is this in the positive? Is the polarity plus on top and minus on bottom? Or is it minus on top and plus on bottom? Well, we know 350 is larger, so really I don't have to subtract that or get rid of it. I can get rid of this second one and create one magnetomotive force. This is just simplified kind of things, but now this 350 will become what we just solved for, 250. All right. So now we just have this, this simple circuit. And we also know that the flux, the red arrow on our transformer core, is going to be going up, and I'll say it's doing this. Flux 1, I'll call it flux 1. Then we have the flux induced by the second coil, which will be going this way. So they're going to be going in opposite directions, meaning they're going to have negative polarity, reverse current, whatever you want to say here. The polarity for the current will be in the opposite direction. Okay, so this was all just to set up our circuit model, but once you get a little better at this, you'll find out making this circuit model is very easy and it's very helpful. The next step here is to create equations for, KCL and KVL kind of equations. So what do we know here? Well, let's solve it for flux 1 first. So we can say 250 is equal to, we'll say flux 1, it's going to be reluctance ABCD plus reluctance G1, air gap 1 plus reluctance of AD. But then we have to do minus flux 2 of reluctance AD because we have two currents flowing through that reluctance. Now we do it for the second one. For the second one, we have minus 250 is equal to I2, or I2 flux 2, reluctance of G2, air gap 2, plus the reluctance of AFED, plus the reluctance of AD, minus flux 1 of reluctance AD. Same thing here. All right, so now what do we notice? Well, they're equal to each other. They have the same magnitude here, but this is just minus. So it's just the negative of it. So we can set them equal to each other and just have one be negative of itself. So, and I'm doing this to solve for the flux because we want to find the flux of the air gap, each one. And if we notice, the flux of the air gap for each one is the flux 1 and flux 2 that I've already determined here. So flux 1 is going, or I'll set them equal to each other here, and ABCD plus flux RG1 plus flux R, or flux reluctance minus flux 2 equals minus, so I'll actually start with flux 1 because it's going to be minus a negative, which is positive, minus flux 2 and reluctances. Okay, well, What else can we do? Well, let's get flux 1 on the left side and flux 2 on the right side. So what we can do is we can subtract flux 1 reluctance AD, and we can add flux 2 reluctance AD to both sides here. So now this will cancels, that cancels, but then we subtract this one over here. That means it gets rid of this, and then we add this one over here. We can get rid of this. Hopefully y'all are following. Plus reluctance G1 equals minus flux 2 reluctance G2 plus reluctance AFED. Okay, so one thing you might notice is, well, we have this negative. That's kind of weird, right? Uh, Not exactly. The reason we have this negative is because the direction that they're going, the polarity of them will be different, but the magnitudes, now the magnitudes we notice are kind of the same. We have, like, this air gap here, and we have also this core reluctance here. Okay, so right now we can't do anything else with this. But what we can do is solve for reluctance. Given the equation, oh, I didn't write an equation. So the equation of reluctance, RT, is going to be equal to the length divided by the permeability times the area of the core, or I guess, or air gap. Okay, so I'll just say reluctance is equal to length of whatever we're trying to do, length of core slash air gap, divided by the permeability times the cross-sectional area of the core or the air gap. So let's find the air gaps first, because that's essentially what we're trying to find, the flux of the air gaps, right? So the flux of the air gap 1 is going to be equal to length G1 divided by mu naught times mu of G1, because remember, mu is equal to mu 0 times mu r, the relative permittivity or permeability times the free space permeability. Well, the permeability of air is going to be 1, the relative permeability, and then we also have the free space, so you don't have to worry about any type of relative permeability for air. Now we have to multiply the cross-sectional area of the air. Well, what did we have at the beginning? Well, we noticed that because we have no fringing at the air gaps, that means the cross-sectional area of the core is equal to the cross-sectional area of the air gap. So what do we have then? Well, that means the cross-sectional area of the core we can solve for very easily. We can see that if we take a cross-section of this square, I'm assuming it's a square, but we have the lengths here. And the depth, which is really nice. So we have the depth here, which is going to be essentially this. And then we have the length going across. So we have this kind of, object. We have 2.5 centimeters, and we also have 2.5 centimeters, right? So we have a cross-sectional area of a square. So it's 0.025 times 0.025. I'll move this over. I'll keep it here, though. And what this is going to be equal to is, let's see, 6.25. 6.25 times 10 to the minus 4 meters squared. Okay, so I'm going to copy this, bring it down here. I'm going to put area of core, because it's going to be the same thing. And what do we know? The length of the air gap 1. Length of air gap 1 is 0.05 centimeters, or 0.05 times 10 to the minus 2 meters. Remember, units are going to be very important in this class. Make sure to get kind of used to writing them. Mu naught, which is 4 pi times 10 to the minus 7. And the units for this are henries per meter. Then we write this here, the area of the core, paste here. And it's going to be 6.25 times 10 to the minus 4. And let's see these units here. So we have meters squared divided by meters here, so that's good. And then meters divided by meters is nothing. or is 1, I guess. And now we can plug this into our calculator, check ourselves. Okay, so I get about 6, oh, that's not a 6, 6.367 times 10 to the 5th. And this is going to be, what, 1 over Henry's? Well, what did we say 1 over Henry's was? Or not really 1 over Henry's. What was reluctance? Amps turns per Weber. So we can say 1 over Henry's or amp turns per Weber. All right, so that's for air gap 1. Well, it's going to be very easy to find air gap 2 because we know the reluctance of air gap 2 is the same equation, except we change out our variables for air gap 2. So we have the length of air gap 2, mu naught, because again, it's the same thing, times the area of the core. So we have, that's going to be something else, but we can copy this other stuff. Okay, what is the length of air gap 2? Well, we see here it's going to be 0.1 centimeters. Okay, again, we can cancel out our units. And we still get 1 over Henry's, which is good. It's 2 divided by. Okay, and I'm going to get 1.273 times 10 to the 6th, I believe, but let me check. Yes, times 10 to the 6th, and again, amp turns per Weber. Okay, now we found the reluctance of the air gaps, but what else do we have in our equation? We have the reluctance of this mean path of the core and this reluctance of the mean path of the core. But what did we say earlier? Or in the problem, it said the reluctance of iron to neglect it. Why is that though? Well, it gives us the relative permeability of the core is infinity. And if the relative permeability of the core, we can say here relative permeability or reluctance of the core is equal to length of the core divided by mu naught times relative permeability of the core times the area of the core. If this is infinity, we get a relative or a reluctance of the core to be 0. So what can we do then? We can say this is 0 and this is 0, which gives us another equation here. Flux of 1 is equal to, or of times reluctance air gap 1 is equal to negative flux 2 times reluctance of air gap 2. Well, we know reluctance of air gap 1 and reluctance of air gap 2. But is that going to give us an answer? That's going to give us more of a ratio. It's not going to give us an answer. So what do we do? Well, if we see here, what can we do here? We can simplify our circuit model, knowing that the reluctance of the cores are 0, meaning if the resistances, quote unquote resistances, are 0, they become short circuits. So what do we have? We have the reluctance of air gap 1. We have our magnetomotive force in the middle, 250 amp turns, plus minus. And we have our air gap 2. Well, what do we notice? You should notice that they're in parallel, meaning the voltage across one is the voltage across the other. So this is going to be very easy to find the flux. We're going to go this way, and the other one goes this way. That means is this flux 1 is equal to 250 amp turns divided by reluctance of air gap 1. Same thing with this. And we can have the negative here because, going in passive or active sign convention here. Meaning again, the magnitude is going to be the same, but the flux will just be going in the different directions. So what we can do now is plug in our numbers, 250 divided by, and we'll do amp turns divided by 6.367 times 10 to the fifth. What is this? Amp turns per Weber. And this is going to be 250 minus 250 amp turns divided by 1.273 times 10 to the sixth amp turns per Weber. In units, what does this happen? Amp turns cancels, Webers comes to the top. So we have a flux of Webers, the units work out, it's perfect. So now the fluxes, plug this into our calculator here, we can figure out 250 over 6.367 times 10 to the fifth. We get a flux of about 3.93 times 10 to the minus 4 Webers. The bottom one. Flux 2, what does this end up giving us? About 1.964 times 10 to the minus 4 Webers also. I think that's right. Hold on. Right? I'm pretty sure. I hope it's right. But anyways, this flux 1 and flux 2 are here. Now what do we do though? Well, we found the fluxes. How do we find the flux density? Well, flux density is going to be units Webers per area, Webers per meter squared. So it's going to be flux divided by the area. We already have the area. This is again the area of the core, or the area of the air gap here. So we have 3.93 times 10 to the minus 4 Webers divided by area of the gap, which is, what do we say, 6.25 times 10 to the minus 4 meters squared. Again, we can just plug this into our calculator, but that's going to be the gist of how to solve this type of problem. Now, it might look like a lot, and it definitely is, but this is going to be apparently worth quite a bit of points. So to be able to do this is very important, especially with all the units. So what I get is 0.6288 Webers per meter squared for the first one. For the second one, I get 0.31424 Webers per meter squared. Okay, so this is that, and this is this. All right, so that concludes, this problem. So hopefully this was okay. Hopefully it made sense. I try to make sure to do it in kind of like a some sort of methodical way. So really just to kind of get back and make sure we understand what happened here is the first thing I did was I took our transformer core and turned it into a circuit model because, we've been doing circuits for the past 3 years. I think it might be a little easier to analyze something similar to this. Of course, there was a quicker way to do this, but just so we, kind of know, this is a very important analysis. Of course, yeah, we could have just at the beginning seen that the infinite permeability means all of the reluctances get zeroed out. So then at the very beginning, we see this, right? But if that doesn't happen in an exam or a quiz, then we know this is the way you do this. You start doing, you start doing analysis, KVL, KCL analysis, using reluctances, the magnetomotive force, and any kind of fluxes. So hopefully this was okay solving it through. If you have any questions, please let me know. Yeah, you guys can always just message me on Discord. Y'all can always comment here if you have any questions. But I'll definitely come out with a little more videos to go over this into more depth. Thank you guys.